Here in the next topic, we are going to discuss the static failure theories for brittle materials. Uh, as we talked, when we talk about brittle materials, we are mainly talking about those materials for which you don't you just abruptly break. You don't have plasticity. So you can talk about plastic strain less than 5%, uh, in true plastic less than 5% in 2 inches, and we summarized this last time. And what when we talk about brittle materials, those are materials that they have suddenly break. You can think the case of a chalk, right? You have a chalk and you just break it and it just broke. It doesn't have room to actually bend, to deform. Very little room for that. So in these cases, with the material properties that we are highly interested in are ultimate compression, ultimate tension, and from these, ultimate compression is always going to be far greater than ultimate tension. It's going to way bigger. And we got three theories that we use. Now, opposed to your ductile materials, in this case, I do need to find my static stress concentration factors, and we're going to call them with B, A, and S. S for torsion, and again, this comes from table A15. Just look what is corresponding, and don't forget that the values that we use for your A and your Z, they actually are given in the table itself. If you look at the table, you will see how to find them. So that's important. Um, in ductile materials, there were one. In brittle materials, they cannot be one. Okay, so these are not equal to one because the stress concentration plays a key role, an important role in this type of problems. As usual, the whole goal of the problem is to do following. We want to find a factor of safety where we want to find we want to find the strength and applied load, applied stress applied. Okay, and your strength is going to be either ultimate compression, ultimate tension, and we will talk more about this type of stress as we move along. And as a review, just remember anything bigger than zero is safe. Anything equal to zero is onset of failure. Anything less than zero will have completely failed. Okay. The overall way that we work these problems, remember the very first thing we do is we have a design factor. If the design factor is not given, take it as 1.15. That's standard. You have to have a strong justification to make it equal to 1. And the very first thing you do in the problem, either you multiply the stresses or the loads by this factor. So my new NXX would be the NXX I get from the free body diagram, right, at the critical load. Remember, this is all at a point. All our analysis we are doing is at one point. Okay, we are not doing the analysis anywhere else. If you're doing uh, your torsion MXX, your moment is also multiplied by your factor MZZ, and you may have your shear rarely used, but many times it is important. Okay, so all these are multiplied by your factors. Uh, so from there on, what you want to do in the problem is second thing, you want to build your state of stress at the point, at the critical design point, at the design point. Okay, and at the design point, then you build your state of stress. Uh, it, just remember that this will be KTA multiplied by sigma XXA plus KTB sigma XX B, and all these will be 0. And depending on the case that you're working with, is that you will, let's suppose, just as an example, if this was XZ, then I will apply my factor TS to my torque, if this actually was torque itself, and everything else would be 0. For this example, this may be here, mass plus minus signs involved, but overall, this is what your straits of stress look like. At the end of the day, as it was in the previous case, we want to find sigma 1, sigma 2, sigma 3. Here we don't find tau max. You can if you want to. Most of your final element software also always basically give you tau max anyways, but these are the 3 components that we need for ductile failure theories. Brittle failure theories. Okay, and then from here on, we just apply the corresponding theory to find what if it is going to be safe or not. Okay, let's move on to the first theory. The first theory, overall, this is what your load diagram looks like. We're going to work with 3 theories in particular. One is the Color-Moore theory, the other one is modified, and the other one is the maximal normal. Maximal normal theory, we don't like to use it and should not be used. We don't use this at all. This point right here is the location of torsion mainly. So what you can look at from the test data, Color-Moore is always the most conservative one. However, it's not worth to add that extra restriction to the problem. Well, all my test data says that this is where my data points are at. So Color-Moore, modified Color-Moore is the one that we really like to use, and that's the one that we strongly recommend that should be used for brittle materials. And this applies at the same as before. Let's suppose I had a load line here and I had several points, maybe a point A, point B, point C, and a point D. What can you say about those points? Well, you know that your point A will always be safe because it's inside the diagram. Point B will be safe and onset of failure for Color-Moore, and point C would be safe because it's still on the line for more modified Moore. However, it will be unsafe for Color-Moore. And this point has completely failed for all of the cases. Okay, so but let's go ahead and work through each one of those 3 theories anyways, and then we will solve in the next set of video, we'll solve an example and see how everything pans out together. The first theory is the maximum normal stress theory, and we don't like to use this theory. This is the non-failure region, whatever is on the inside. Your book calls it sigma B, but maybe I like to call this sigma 3. It's probably less confusing, sigma 1. Okay, so this is what I like to call it, sigma 1 and sigma 3. And basically, uh, the problem with this theory is that historically in the old days we used to use it because it's very simple to use, right? You just know what things are happening. However, we have found that in this particular quadrant, it is not safe. Okay, using this theory produces not unrealistic results, and we can see from the test data, right? If you say, "Oh, I got all this space left here, I want to design something here," but you actually test data shows that you have way failed. That's why we don't like to use this theory. However, we can do that. And how we program this in Matlab, Matlab programming actually is quite simple, involve these criteria, and they're given in your textbook. You can use them. We will do a couple examples to see how this works. Uh, the Brittle Color is the most conservative one, can also be used, and it's kind of very simple to use as well. Basically, this is your compressive, this is tensile, right? And we just draw a straight line. This is ultimate, by the way, SUT. This is SUC. This is ultimate tensile compression. For brittle materials, we don't have yield. We only have ultimate. So this is the region that we are using. These are the equations. And in MATLAB, it's very easy to program that. It's a simple equation. And depending on the case, we got 3 different cases. We just apply them. The last theory that we use is the modify more. Modify more is this one right here. So this one, so it makes it a little closer to your test data. And this is the failure criteria that these are the cases in which you use. So if you are in this quadrant here, use this criteria. If A is positive, so if A is positive and B is negative, so you're talking about this criteria. If these are positive, then it's going to depend on also this ratio, that these are the equations that you use, or if it's less than this, then you use this. There are 2 different formulations for this. The first formulation is the one that your book recommends. However, there's a second formulation for the same problem that your book doesn't discuss, but it's very, very popular and people use it all the time. It's called using the effective modify more. The effective modify more is nothing else than calling C1 times this quantity here. And the whole thing is divided by 2, C2, C3. And then what you want to do is you want to choose the maximum value between C1, C2, C3, and the maximum stresses. Okay, we don't use absolute values here, by the way. If this value is bigger than 0, then use this equation. Actually, we can say bigger or equal than 0. That should be good as good enough anyways. But if it's less than 0, then you're going to set that equal to 0 and know that if it's 0, it goes to infinite. Okay. Before we move on to some examples, what we have is we got the brittle failure, we got the ductile failure, and depending on the cases, that's what we use. If it is bigger than 0.05, a 2-strain, then we actually ductile region. If they are approximately same, then you're safe to go on this route. If they are not the same, then you may be stuck with color more. However, I should mention that this theory is very popular. This is the one that we use. Experimental test data has shown that this works, and people in the industry use this all the time. This is the famous, what people call von Mises. This is the same as the distortion energy stress. In this side over here, people use this one all the time. This is very popularly used, matches the test data, and we have something we call sigma effective. Here we call this sigma equivalent. So this kind of summarizes basically how brittle and ductile materials actually work together. Um, Given these charts, the next thing we will do is we will discuss one or two examples to better understand this problem.